Okay, I will briefly introduce this ICML paper titled, How Does Information Bottleneck Help Deep Learning? This paper is written by Kenji Kawaguchi, Zhun Deng, Shu Ji, and Jiaoyang Huang. Overview. Numerous deep learning algorithms have been inspired by and understood via the notion of information bottleneck, where unnecessary information is, often implicitly, minimized while task-relevant information is maximized. However, a rigorous argument for justifying why it is desirable to control information bottlenecks has been elusive. In this paper, we provide the first rigorous learning theory for justifying the benefit of information bottleneck in deep learning by mathematically relating information bottleneck to generalization errors. Our theory proves that controlling information bottleneck is one way to control generalization errors in deep learning, although it is not the only or necessary way. Illustration. We use X and Y to denote the inputs and targets to deep nets. For example, X is an image of a cat, and Y corresponds to the class label of a cat. We also use Z to represent the output of a hidden layer of a deep net. We provide a new type of generalization bound. Our new generalization bounds scale with the information bottleneck, or more concretely, the conditional mutual information between X and Z conditioned on Y. This is very different from the previous generalization bounds that scale with the number of parameters, VC dimension, radiometric complexity, stability, or robustness. Background. In practice, the conditional mutual information is often minimized implicitly, for example, as a result of stochastic gradient descent or an architecture choice. Thus, the notion of information bottleneck provides a perspective to understand deep learning in general without explicit use of the information bottleneck principle. An explicit minimization of the mutual information has been also adopted in the machine learning literature as a regularization technique. Despite these backgrounds, there is no rigorous generalization bound for information bottleneck, although there are several conjectures without complete proofs. Our results, number 1. In this paper, we first prove that when an encoder is pre-trained and independent of a downstream training data, the generalization error of the downstream task scales with the conditional mutual information between X and Z conditioned on Y. Moreover, it approaches 0 at the rate of 1 over square root of n as desired. Here, recall that X is an input, Y is a target, and Z is a hidden layer output. A more detailed and non-asymptomatic finite complexity bound are presented in the paper. Our results, number 2. In this paper, we also prove the following. In general, when an encoder is potentially dependent of the downstream training data, the generalization error of the downstream task scales with the conditional mutual information between X and Z plus the mutual information between the encoder function phi and the training data. Here, recall that the function phi represents the function implemented by the hidden layer. In other words, Z is an output of phi given each input. A more detailed and non-asymptomatic finite complexity bounds are presented in the paper. Our results, number 3. We also investigate the merit of our new mathematical findings with experiments across a range of architectures and learning settings. In many cases, generalization errors are shown to correlate with the degree of the information bottleneck, that is, the amount of unnecessary information at hidden layers. In this plot, the y-axis corresponds to the degree of the mutual information present in our generalization bounds, whereas the x-axis represents the generalization errors. That's all. Thank you.